domain of inverse function, compute the range of the original, and those two should agree. And let's just see if that actually happens for the function whose inverse we computed at the end of last time. So last time we said that the inverse to this rational function was that rational function. Well, hopefully, because I literally just copied it down from the previous page. And let's see if that seems to hold up. First, just, this is what I want. There are the Desmos graphs. Do those two red and blue graphs seem to differ by swapping the roles of x and y? Cool. Let's see if this domain and range issue holds up. So let's take a look at the original function. Either by looking at that graph or by looking at this formula, what's the only thing not in the domain of that function? 2. Graphically, you can see that because there's a vertical asymptote. Algebraically, you can see it because you divide by 0 if you try to plug in x equals 2. So that means that ideally, the only thing not in the range of the inverse function should be y equals 2. And I'm going to put a question mark there for now to see if the graph seems to hold up. So there's the graph of the inverse function. I would like to know, is an output value of 2 achieved by any x value? Are there any actual x values where this graph touches that green line? Cool, so that output value isn't in the range. Let's do the same thing. Well, so that means that the domain of the original function is actually equal to the range of the inverse, which is what you expect should happen. Let's see if the reverse happens. So looking at that graph, it looks like the only thing not in the range is the location of that horizontal asymptote. Where is the horizontal asymptote of this? Let's do the quick check. So forget about the graph for now. Does this rational function, the one I'm pointing at right now, have a horizontal asymptote?
Yeah.
Yeah. Degree of the numerator is the same as the degree of the denominator. When you're in that situation, how do you find the horizontal asymptote?
Isn't it just 0? Wait.
That's when the denominator is
bigger.
bigger.
No, it's the coefficient divided by the coefficient, right?
Yeah, cool. So what's that for this one?
You just put 1.
Cool. And even when you don't remember that trick, in general, if you just want to think about horizontal asymptotes, you're thinking about plugging in a gigantic number for x. So if you imagine you plugged in 1 billion for x, you'd see 1 billion minus 1 divided by 1 billion minus 2. The minus 1 and the minus 2 don't make a difference. So that means that the only thing not in the domain of the inverse function should be x equals 1. And there's the formula for the inverse function. Does that agree? Nice. So there's that check done. Here's now the technical bit I want to get into. So all that we've done so far is what the inverse function is supposed to capture. It's supposed to be the new function you get by undoing the old function. Here's the very mathematical technical definition. If I give you a function f of x, and I tell you that f inverse of x is the inverse to that function, well, this is the unique function which satisfies these two facts. F inverse of f of x is equal to x for every x in the domain of f. And let's see if that just seems sensible. So f of x is what happens when you take the input x and do f to it. So you start at x, you do f, then you undo f. That should get you back to x, right? Get you back to where you started? Yeah, that's why that should be x. Similarly, if you start at some x value and undo f, and then you do f, then you're back to where you started. So those two things should be true. And that now gives a formulaic definition of what it means to be the inverse function. So if someone asks you to check that a function is the inverse to this function, here's what they're asking you to do. So we got f inverse of x to be this pink function, 2x minus 1 over x minus 1. So this exercise is asking you to check that this is actually the inverse to this function by verifying these equations. So this problem is saying, well, we need to check that we have f of f inverse of x is identically equal to x, and f inverse of f of x. So two compositions are each identically equal to just the input value again. So this is like two equations we need to check. Does that look like the type of thing that you know how to check? Cool, let's go through it. So this is like, I'm asking you to compute and simplify a composition, and I'm telling you what the end result ought to be. And if you don't just get x at the end, then something's gone wrong. So let's go through. I think I'm only going to do one of them. In order to really check that something is the inverse, you need to check both of those equations. I bet checking either one will involve similar amounts of work. Which one should I do? The leftmost one or the rightmost one? Leftmost? Rightmost? Cool. It's the same amount of work either way. I think there were more people who said rightmost, but that may have been an artifact if that's the second one I asked. So, let's check this one. Maybe I'll number these. Checking 1. So we need to compute f inverse of f of x. And I really, really want the end result to just be x. Well, we've got a formula for what f inverse is supposed to be, right? It's 2x minus 1 over x minus 1. So this will be 2 times, maybe some color coding will help, f of x minus 1 all over f of x minus 1. So all I've done there is I've like used the formula for f inverse, I plugged f into it.
Is there a minus 2 on the bottom? Fx minus 2.
So what I wrote here, let's see if what we got.
We plugging.
Yeah, so
Oh,
maybe.
my fault, my bad.
Yeah, so I think what you are doing is you are like you were writing down the thing that would have gone there, which is another thing that would be needed to do to complete this problem. Like you need to do both. I'm only going to do one. All right, cool. So far so good. We've got a formula for f of x, right? Let's use that formula. Big fraction 2 times x minus 1 over x minus 2. And now what's the whole game? I know in my heart what this should simplify to. This should simplify to just being x. Let's see if we can get this to simplify down to just x. So in looking at this expression, what seems like a reasonable next step if I just want to simplify that? There are a few sensible answers. One of them is like the more mechanical and robotic one. The other one's the one that'll save us some work later on. So if you want to see that, what would you want to do to that if you wanted to simplify? Let's focus on this. So if you just look in the numerator of that big fraction, I see a fraction minus 1. Whenever you see a fraction minus 1 and you want to like simplify it, you need to get a common denominator. That way you can subtract fractions. And then do the same thing in the bottom of the thing. So let's get some common denominators. In doing that, so let's get a common, in fact I don't like the word simplify there. Let's say explicitly what's happening. get a common denominator. And maybe also distribute this too. So that'll be 2x minus 2 all over x minus 2 minus x minus 2 over x minus 2 all over x minus 1 over x minus 2 minus x minus 2 over x minus 2. So far so good? All I've done is I've replaced those two ones with other things that are equal to 1. Right. This is the same as that. And then I've also said, well, how do you multiply a fraction by 2? You multiply the numerator by 2. 2 times 1/5 is 2/5. And the whole reason to get a common denominator is so you can subtract fractions. So let's subtract those fractions. How do you subtract fractions once they have a common denominator?
Just subtract the numerator.
Cool. All right, so let's do that. 2x minus 2, I guess I also need to distribute this minus sign, minus x plus 2 all over x minus 2. I'm going to add some parentheses so I know exactly what is in the big fractions denominator. X minus 1 minus x plus 2 all over x minus 2. Yeah.
Why is it x plus 2 now?
Why is it plus 2? So, when you distribute this minus sign, what'll happen is you'll turn that into a plus. Now that will be minus x. Distribute the negative sign, double negative becomes a positive. Is that the plus 2 you are asking about?
Yeah.
Cool. And then the same thing in the top, that's where that plus 2 came from. Cool. Feel okay so far? All right. And we just want to simplify this, so like, what do you see that might be helpful to simplify?
Both have the same denominator.
Both have the same denominator. So I see something divided by x minus 2 all over something divided by x minus 2. So the x minus 2's will cancel? Nice. Whenever you see a single thing multiplied or divided by everything in the numerator and everything in the denominator, they cancel. And let's just see what else cancels. What else do you see that might cancel or simplify? Or should we just like copy down the next thing? We could. Cool, I'll copy down the next thing, and then we'll see what we notice. 2x minus 2 minus x plus 2 all over x minus 1 minus x plus 2. Cool, what next?
With minus x plus 2, maybe?
Yeah, let's look in there. So let's just look in the numerator of that fraction. I see a couple different x terms and I see some constant terms. Let's just try to combine combine the similar terms, some of them will cancel. Minus 2 plus 2 is 0. See anything similarly helpful in the bottom of the fraction? All right, so let's see what we get. 2x minus x is x. Negative 1 plus 2 is 1. This simplifies down to just x, which is what I knew it should do. So that's now half of the walk done to verify that this is in fact the inverse to this function. So now I'll tell you like what the homework associated with Monday's lecture was to do exactly this. So repeat this analysis to verify that a rational function has the advertised inverse function. That's what one of the homework problems is for the open-ended last time. People feel good about that? Nice. And you'll notice that was like a lot of steps, but like sometimes simplifying takes a few steps. All right, so let's start in on a new item on the docket today. let's start talking about exponential functions. Any nuts? Downside of sitting close to the front when I hand things out, like slightly before the start of class. Cool. So, let's see, if I say the word exponential function, how many people have an idea what I already mean? Cool, let's hear it. What is an exponential function? Yeah.
Like drastically increases.
Yeah, it's a function that like increases fast. There are functions that increase faster, but it's also faster than like any polynomial growth function. If you write down a polynomial, an exponential will beat it. What are some other thoughts people have about exponentials? Well, how about this? Maybe I'll even just like, let's just see this warm-up example for what an exponential is. And hopefully it'll feel reasonably familiar. If not, that's okay. So, let's talk about the trouble with triples. So, you begin with a single triple, a very small, cute, fuzzy animal. These have the troubling property that they reproduce very fast. After 1 hour, that one triple will split into 2 triples. Each of those 2 triples will split after another hour into 2 triples each, so 4 triples. So let's just fill in the population track that this thing will take. If you start with 1 triple at time 0, after 1 hour, you'll have 2 triples. After 2 hours, that will double to 4 triples. After another hour, those 4 triples will each have doubled. So you'll have 8 triples. At hour 4, how many?
60.
Cool. At hour 5?
32.
So what's like the rule that's getting you the number of triples after n hours?
Divide by 2.
Yeah, you just keep multiplying by 2 enough times. So number of triples after n hours is 2 times 2 times dot 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 times 2 n times. And that's an annoying enough thing to write, and a common enough thing that you need to talk about, that is what we'll mean by 2 to the n. And in fact, you already knew that, right? Like, what does x to the 5th mean? It means x times x times x times x times x. In this case, we're just thinking of the thing in the exponent being the thing that grows. How about this? After 2 days and 1 hour, after 49 hours, how many triples do you have? So that would be very annoying if you wanted to do it by hand. You'd have to like multiply 2 by itself that many times. So we'll resort to a computer. The standard computer notation for this, there will be some like upper caret symbol, and if you want to ask a computer to do that. So, I don't know, maybe just for the sake of demoing, it's really big, yeah. So that's 2 raised to the 49, because 2 days and 1 hour is 49 hours. Now let's even talk about that notation. So this is giving an answer of, in scientific notation, (5.62 E14). And let's talk about what that even means. So when you have numbers that are just really big, like the ones digit doesn't actually tell you much about this population, right? You don't care about the ones digit. You really care about the biggest digits. So you just record the biggest digits and then how many digits there are. That's what this notation means. You interpret that as 5.62 times 10 to the 14th. Or if you really wanted to write it out, 562, and then a total of 14 digits. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 14. Assuming I didn't lose count while I was writing down digits. Is that actually 14 digits? Cool. Yeah, that's cool. All right, cool. So let's ask this question too. After 6 hours and 20 minutes, how do you compute the number of triples there are? Let's start with this. 6 hours and 20 minutes. We have like a formula for the number of triples after n hours. How much of an hour is 20 minutes? If you were to like write this as a fraction, a third. So that's like 6 1/3 hours. Or if you happen to like decimals, 6.33 hours. So, if you wanted to have a computer tell you how many triples there will be, the computer is perfectly happy to do that. Two to the 6.333 is about 80.616.
Yeah. I know, like, the biggest problem with that, wouldn't that be kind of like impossible if they split only after an hour and like have like a third split?
Yeah, cool. So here's a reasonable objection to make. If you read this problem very literally, it indicates that right at the hour is when they split. Literal interpretation. Right at the hour they split. In which case the population should just be 2 to the 6. Which, on the one hand, like, I would encourage you to like internalize your powers of 2 up to like 2 to the 10. It's just good to know. 2 to the 6, 64. You would say the population is just 64, and then you have some that are on their way to producing more triples. And in fact, an answer of 80.616 is silly anyway, isn't it?
Yeah.
It's like you can't have a fractional number of triples. And this is always a problem when using continuous mathematical models to measure certain things like populations. Populations are discrete. You can only have a whole number of individuals in a population. And so that's always like a hurdle that mathematical biologists run into. Like any model you use to do something biological is going to hit some stumbling blocks at places like this. So maybe you would interpret this as saying, well, maybe the triples, like, they split approximately every hour. Like maybe there's some leeway, there's some like normal distribution that it's on average an hour that takes them to split. In which case, this like 80.616, your prediction would be, I predict the population after 6 hours, 20 minutes, will be pretty close to 80 and maybe a half. So maybe like 81, somewhere between 80 and 81. Would be like how you would interpret the result we got in model. Does that feel okay? Yeah. So that's just an issue you have to deal with whenever you use exponential growth to model populations. They'll wind up giving decimal answers when you plug in non-whole numbers, and you need to figure out how to interpret that. Because, yeah, admittedly, this is like a made-up, silly toy example, but any population isn't going to reproduce on such clockworkers on the hour every hour. Cool. People feeling pretty good? All right, so let's talk about exponential functions in detail. So what is an exponential function? That's me. And I think here's the definition I'm going to give. So for whole numbers, you know exactly what exponentials mean. 2 to the 5th is 2 times 2 times 2 times 2 times 2. Pi to the 5th is pi times pi times pi times pi times pi. As long as that exponent is a whole number, you know what exponential should mean. B to the n is just b times times b. Where how many times do you write down b? You write down n times. Cool. Let's talk about negative powers. Let's think about what a negative power should mean. So b to the fifth means that you just multiply b by itself 5 times. B to the negative fifth should mean you anti-multiply b by itself 5 times. And what's anti-multiplication? Divide. That's all it means. If you have a negative power, then you want to divide by b that many times. And now there are a few ways to write that. So instead of thinking about that, you could think of that as 1 over b to the n. Or if you like, you could think of it as 1 over b to the n. If you see a negative power on the exponent, you can think of it in terms of positive exponents in division. Feel pretty good? Nice. The 0th power. Let's think about what the 0th power should mean. So like b to the 4th should be b, right? You take b and just like write it down once you have b. But that should also be what you get if you started b to the 0th. So you don't multiply by b any times, then you multiply by b once. That tells us what b to the 0 should be. B to the 0 should be something that when you multiply it by b, you get b. So 1. B to the 0 is 1. With one caveat, provided that the base is not 0, you are not allowed to talk about 0 to the 0. 0 to the 0 is not mathematically well defined. Because that logic that I made, like, what's a number that when you multiply it by 0, you get 0? Like, what are the answers to that question? Anything. So the rationale I just gave says that 0 to the 0 can be anything you want. And so we just don't talk about it. It is not something that mathematically makes sense. If you think about it the right way, you can get like 0 to the 0, like maybe it should mean e, Euler's number, because that's this number that creeps up a lot of times when you don't expect it. But we just won't define it. It doesn't mean anything. Rational powers. So before I think about rational powers, let's actually think about this. Let's think about like b to the 1/2. So that should be like what you get when you multiply by b half of a time. So I guess that means that if you multiply by b half of a time and then you multiply by b half of a time again, you should get b. So b to the 1/2 should be something so that when you multiply it by itself, you get b. What's a thing whose square is b? That was too much. Yeah.
I have a question. So you said that b cannot be 0?
Yeah, if b is 0, then I won't allow you to talk about b to the power 0. You can talk about 0 to the 5th, that's fine. But you can't talk about 0 to the 0.
I plugged that into the Google calculator and it said it's 1.
Well, okay, so it's making a conventional choice.
Is there like certain times where it would be 1? Because that wouldn't?
So I'm gonna make a bit of a tangent based on this. So, in order to try to decide what 0 to the 0 should mean, well, here's one argument. If I take that should give me a pretty good guess as to what 0 to the 0 should mean. Right? So let's compute that, because that's something that we know how to well. By the end of this thing I'm writing down on the page right now, we'll know how to make sense of. So, let's do that. Yeah, at least 2. Pretty close to 1. And let's get those numbers to be even closer to 0 by sticking some more digits here. Even closer to 1? Well, so let's play with that logic. What if I increase the number of zeros at a different rate? That should still be close to 0 to the 0, right? That's close to 0, that's close to 0. So what if we do this? Let's just throw in like 3 extra zeros in the base of the exponent. And now we'll keep on playing that game. Am I doing this right? Oh, Chris, what's wrong with you? Stick 2 there instead. Because that should also be pretty close to 0 to the 0. So let's see what happens when we do that. 0.002 raised to the don't think I need these parentheses, but I'm sticking them there anyway. So the idea is that like, there's the graph of x to the x, so when you get close to 0, it should be getting close to 1. You see that from the graph. But there's, I think, what I... Cool. I'm getting lost on this tangent, which is not relevant to us right now. Remind me, maybe at the start of next time, to continue this discussion of 0 to the 0. My brain is freezing. You can come up with arguments based on this that say that 0 to the 0 should be anything you want. Okay, I'm not going to do it right now. Because then, like, I just lose the whole lecture on me, like, trying to remember something that I know. And, like, I will not allow 0 to the 0 to be something that I talk about in the course of this class. Except under, well, okay, let's give one circumstance in which I would. So when we talk about polynomials, like, I always talk about x to the constant term as being, like, kind of like x to the 0. But that only makes sense really as a constant if you do allow 0 to the 0 to be 1. And so in that sense, yeah, I absolutely allow it. But there's some weirdness you can get into if you do. Cool, let's talk about fractional powers. Let's talk about b to the 1/2. So this should mean like, what do you get if you multiply b by itself half of a time? So what's like half of the way to multiplying a thing to get b? I'm gonna write something down, and it'll help with the motivation.
Dividing by negative?
Dividing by a negative, well, no, there's no like negative insight there. I'm gonna call that star for now. So whatever this thing is, it should be like half of the way to being a thing that when you multiply it by, when you just write it down, you get b. So it should satisfy that if I multiply this thing by itself, I should get b out. So what's a thing that I can multiply by itself to get b? What's the thing whose square is b?
Square root.
Square root. So fractional powers mean roots. And I was trying to build towards that, but that's just the convention. If you see b to the 1/2, it means the square root of b. If you see b to the 1/5, it means the 5th root of b. If you see b to the p over q, you'd interpret that as saying, we'll start with b, I'll raise it to the pth power, and then I'll raise it to the qth power. So that's the qth root of b raised to the pth power. Whenever you see a fractional power, the denominator tells you what root you need to take. The numerator tells you what power to raise it to. That feel okay? And like if you see something like that written down in the wild, it's not going to be something you're going to compute by hand. You're going to ask a computer to calculate that by saying, well, what is 5 to the 3/2? But some things you can compute by hand. Let's compute the things we can compute by hand and then use a computer for the things we can't. 2 cubed. What should that be?
8.
8. Right, because it should be 2 times 2 times 2. Nice. What about 4 to the power negative 3?
1 to the 64. Or 164.
Yeah.
Yeah.
I listened to what you meant. That feel good? Because 4 times 4 times 4 is 64. 8 to the power 5 over 3.
Cube root 8 to the 5th power.
Nice. So that should be the cube root of 8 raised to the 5th power. And you'll notice that I wrote them in the opposite order as is down there. It doesn't make a difference. That's the same thing as the cube root of b, then raise it to the 5th power. What's the cube root of 8? 2. So this should be the same as 2 to the 5th. What's 2 to the 5th?
I don't know. It's like,
Is it promised you?
I think so. Yeah.
We have it on the previous page.
Yeah.
Nice. And if you want something fancier like e to the square root of 2, well, to get that, I can't compute that by hand. For starters, I can't get a good enough hold even of the square root of 2 by hand to do this computation. Yeah.
Quickly explain how cube root of 8 to the 5th would correlate to 2 to the 5th. Just quickly run me through how.
Yeah. What's the cube root of 8?
Just 2 and then 2 to the 5th. Okay, that makes sense. Next.
Yeah, so the question was like, how did this become that? Well, the thing underlined in orange just became the thing underlined in orange. What about e to the square root of 2? Well, to do that, like, really you do just need to resort to a machine. It's somewhere around 4.11. And what is Euler's number? E is Euler's number. It's somewhere around 2.72. It has an important role, especially if you're doing something that has to do with exponentials. Euler's number is the base of the exponential that, if you like, has the most natural growth rate. In that e to the x is its own instantaneous rate of change, which isn't something we talk about in this class. We'll talk about average rates of change. The extra credit at the end of this packet is going to explore like, what is e to the x and why is it the best exponential? But for now, let's go back to base 2. Let's talk about 2 to the x again. Let's try to generate graphs of exponential functions. And to do that, let's just do it. What's 2 to the 0? 1. So if you want to graph 2 to the x, that means when x equals 0, you should have y equals 1. And I think I'm going to do whole numbers first. What's 2 to the 1? 2 to the 2? 2 cubed? 2 to the 4th? Nice. Let's plot those. 2 to the 1 is 2. 2 to the 2 is 2, 3, 4. Next one is 4, 5, 6, 7, 8. Next one is 16, so 8, 9, 10, 11, 12, 13, 14, 15, 16. So you see that that's growing pretty quick. In that if I went one farther to the right, the y value would be way off of the graph. If I went one more to the right after that, I'd probably be off the page. So yeah, exponentials grow fast. That's one of their properties. Let's do negative powers too. What's 2 to the negative 1?
Be 1/2.
1/2. So there-ish. 2 to the negative 2?
1/4.
1/4. Or 0.25 if you like. Graphically, I guess that's half as high as the dot to the right of it. 2 to the negative 3.
1/8.
And then 1/16. So, let's interpolate between And that will give me a pretty decent graph of what 2 to the x will look like. And I don't know, before we go on to some algebraic things, let's just look at that graph. Yeah.
Would 0 be an asymptote on this graph?
Yeah, let's think about it. Y equals 0, you mean, right?
Why is it 0, yeah?
So let's try to think about that. So does the graph drawn seem to get really close to a y value of 0?
Yeah.
Yeah, that's what a horizontal asymptote means. So yeah, this thing has a horizontal asymptote at y equals 0. But maybe you notice one thing that's weird compared with rational functions. It's only a horizontal asymptote on one side. In that, as x goes to negative infinity, the y value goes to 0. Which is the opposite of what you see with rational functions. Rational functions are very symmetric when it comes to their asymptotes. Exponentials, though, are not rational functions. So let's start writing down some of the exponential algebraic laws, which are just what's the algebra that exponential functions do? And all right, you need those if you ever hope to do algebra to these things. So let's start building those. Let's write down what is 4 to the 7th times 4 to the 2. And I'll write down what it is, then we'll notice what it simplifies to. So let's start with 4 to the 7th. That is, of course, 4 times 2, 3, 4, 5, 6, 7, with multiplication symbols in between, times 4 times 4. And I put those parentheses there just to be careful, make sure I'm not cheating myself out of anything. But now that I've written that out, do those parentheses matter? No. Multiplication on its own is associative, so if you just have things multiplied together, you can do it in any order you want, the parentheses don't matter. So how many 4s do you see written in a row? 9. Which coincidentally is the same thing as 4 to the 7 plus 2. And was there anything special about any of the things that I wrote down there that made that happen?
Is that the same base
Oh yeah, the same base, that's important. But otherwise the exponents could be anything you want and you'd still get this addition property. So whenever you multiply two exponentials with the same base, you just add the exponents. And in order to see an opportunity where that's useful, let's use that to compute 3 to the 3 halves times 3 to the 5 halves without using a machine. So, to do that, let's see. Do they both have the same base? Cool. So the exponents should add 3 to the 3 halves plus 5 halves. And what is that total number you see in the exponent?
Wait, 8 over 2.
8 over 2. 4. Okay, cool. Are we happy at 4? Nice. So it's 3 to the 4, and I guess we could even compute that by hand. All right, that's not so many 3's written in a row that you can't just handle it. What's 3 times 3? So this is 9 and that's 9. What's 9 times 9?
81.
Cool. There's a computation you can now do just by hand. And that's noteworthy because if I asked you what is 3 to the 3 halves, you'd say, well, it's going to be 3 cubed, so 27, and then you take the square root. It's the square root of 27. Yeah.
I don't know how I got 7 2%. So I did 3 times 3, 9, 9 times 3, 27, 27 times. Oh, never mind. I had it wrong.
Cool. Yeah. And all right, like whenever you're multiplying numbers together, some stuff can go sideways. The next exponential law I want to state is, well, what happens when you exponentiate and then exponentiate again? And to see what that should be, let's just do it. So if I do 5 to the 4th to the 3, that should be like 5 to the 4th times 5 to the 4th times 5 to the 4th. And I'm going to expand that out. It's going to take like some space. All right, each of those 5 to the 4ths I can replace with 5 5s in a row, 4 5s in a row. 3, 4, 5. 1, 2, 3. 1, 2, 3, 4. All right. And again, like, do the parentheses actually matter? No. Multiplication is associative, so it's fine. How many 5s do you see? 12. In fact, you explicitly see 3 sets of 4, which is what 3 times 4 means. Whenever you see a double exponential, you just multiply the exponents. That feel pretty good? Nice. And I have 3 minutes left on the clock. Let's use that to do some algebra. Let's try to solve an exponential equation using this fact. And here's the strategy I'll go for. So if everything had like the same base, I could simplify. So let's try to realize everything here is something that has the same base. What seems like a useful base that everything has in common in this problem?
Which problem?
The one I have an arrow pointing to. Realize 32 and 4 as powers of 2. So I guess that tells you the answer I'm looking for. Everything inside is a power of 2. So one could rewrite this problem as 2 squared to the x equals 2 to the 5th, because 32 is 2 to the 5th. And on the left-hand side of that, I see an exponential of an exponential. So how should I rewrite that 2 to the 2 to the x using that idea?
2 to the 2.
2 to the 2x. All right, and so let's think about that. So that means that 2 to the x, 2 times x and 5 are both numbers, and when you plug them into the exponential with base 2, you get the same output value. So let's try to think about how that could happen. There's the graph of 2 to the x. Does that look like a one-to-one function? Does it pass the horizontal line test?
Yeah.
Cool. So that means the only way that 2 inputs can result in the same output is if those 2 inputs are actually the same, because this is a one-to-one function. So this simplifies. Whenever you see a one-to-one function on each side of an equal sign, you can just erase it. Does that look like an easy equation to now solve? What's the solution?
5 and 2.
X equals 5 over 2. Or 2.5 if you like, or 2.5 if you like. They're all the same. So using these ideas, you can solve some equations that you couldn't before by getting common bases. And I'm about at time, but do you think you could do something similar for 9 to the x equals 27? Everything there seemed to have a common base. What base are you thinking of? Cool. What if I asked you to solve 5 to the x equals 7? Could you apply that same trick there? No. So we need a different tool. That tool is logarithmic covariance. Groovy. So I find myself, yet again, falling behind schedule-wise. I'm not going to like tweak homework deadlines or anything yet, because everything's just due the Friday of the week after it's assigned, so if it's assigned today or tomorrow, it doesn't matter. Once Friday rolls around, I'll decide if I need to rearrange any of the deadlines. Yeah.
How many did we do today? I have some of the extra credits and then also 2 added questions on the March 6th open-ended.
Oh, nice. Can you make my office hour?
Is it 1 and 2 today?
Yeah.
From 1 to 4:20 I have class. So I don't know if you have. Because you have class after this at lunch, I could just meet tomorrow too. There might be a better time to do that.
Yeah, if it doesn't need to happen today, then
Yeah, because I mean, it's not due
let's-
till Friday, so it doesn't really matter.
yeah. So I think here is what I would say. You can shoot me an email. With like just like the question, I can send you whatever guys. It's not a perfect following communication for this, but email.
But it
is
works,
okay. So send that along, and then would you rather my office hour, which is 1 in the afternoon, or 8 in the morning?
I just come tomorrow at 1 in the morning, so I don't have that class.
1 in the afternoon. 1 in the
Yeah.
afternoon. I won't be here.
1 in the morning, sorry, yeah.
Okay, cool. I'll see you in my office hour tomorrow.
Sure, thank you.
Yep.